Consider man in the orange box. Can we predict where he will move next? This prediction problem has been tackled in computer vision and robotics to model human behavior from third-person view. But a question is whether this prediction really models how we perceive and behave. I argue that if you like to understand his behavior, we should put yourself into his shoes, or we should be able to answer the following questions. If I were him, how would I move into the scene? But the third-person prediction cannot answer this question because we cannot experience what he is experiencing. Then what is he experiencing visually? This might be the image he sees from his perspective, with depth of course. We perceive the scene such that a strong emphasis is on the short-range area. Occlusion reasoning is done by my perspective. We perceive and behave in relation with me. For instance, what does the stop sign mean to me? Such question cannot be answered by the third-person prediction. Therefore, in order to predict human behavior, we should use a first-person view by putting yourself into his shoes. In this paper, we present a future localization predicting future ego motion from first-person RGBD image. The heat map represented the likelihood of future location. This shows overall trajectories. Then why future localization is challenging? Consider an image with a future trajectory. The testing scene is similar to the training image in terms of visual semantics and geometric configurations. Therefore, we can predict the trajectory by copying it from the training image. But this is not geometrically correct because two images has a different head orientation. One looking down, one looking forward. Geometric correction cannot solve this problem because now it is semantically wrong. In this paper, we use the ego rational representation and preference learning to address these challenges. Consider a man with a first-person image eye. He will navigate the scene by planning his trajectory on the ground plane or configuration space using first-person image eye. We construct the ego rational configuration space by projecting image onto the ground plane. The projected image is a global centric representation measured by the first-person image. This representation is a head orientation invariant. This is very important for first person because we move our head significantly. We encode two information in a configuration space. First, we encode the RGB value measured by the first-person image eye. And we also encode the height of the occluding object, which is a global central representation, measured by depth image. Inspired by proxemics, the configuration space is represented by the log polar coordinate, which produces retinal representation. This representation is persistent in 3D because it is a head orientation invariant. And it is persistent in 2D because projection of unit distance in configuration space does not introduce severe perspective distortion in first-person image. This produces our ego retinal map in the middle. In the same way, ego retinal map for the depth image can be computed, which encode the height of the occluding objects. This representation has three properties. First, it is head orientation invariant, and it is persistent in 2D and 3D distance, and it reasons about the occlusion. Here we compare ego retinal map with other representation used in computer vision and robotics. Cartesian coordinate image produces severe collapse in long-range pixels. More importantly, it is not head orientation invariant. Therefore, it is not suitable for the representation of first-person image prediction. Cartesian in ground plane has been widely used in robotics because it produces global central representation. However, it collapses short-range pixels severely. It can only model one destination because there exists only one vanishing point. Our representation can model infinite number of destinations, and it is persistent in 2D and 3D distance. We learn an ego retinal map using our dataset captured by first-person stereo cameras, which produce ego depth images. For each training image, we can associate with a future trajectory because the camera wearer already has been there. Trajectory is a label which can be computed by the structure from motion. Note that no manual supervision is required. This dataset includes various scenes such as mall, commute, downtown, and cafe. We represent a future trajectory on a configuration space. In addition to the polar coordinate, we encode the spatial distribution of the obstacles around the trajectory. Omega is a vector toward the near obstacles computed by depth map. This reflects the topological structure of the trajectories. For instance, trajectory A and B are spatially close but topologically different. Here we visualize the topological structure of the trajectories in space. We learn walkable pixel by associating trajectory with image. On the top right, transparency of the image indicates the walkable pixels. We also learn height of the occluding object from depth image. In prediction, given a test image, we retrieve trajectory by associating with ego-retinal representation using k-nearest neighbor search. We predict the trajectory that minimizes following cost. Data cost takes into account the distance from the retrieved trajectories. We want a predicted trajectory to be preserved walking preference presented in the training image. Depth costs account for the walking preference over occluding objects. And RGB costs reflect walking preference over pixels. This optimization allows us to adapt the retrieved trajectories onto the training image. This results in a future localization. On the bottom right, we visualize the ego-retinal map with the predicted trajectories. Note that we perform the perception and prediction task in the same ego-retinal representation. We evaluate our prediction by comparing with other representations. Cartesian image produce error rate 0.7 meter per second, which produce 7 meter error after 10 seconds. Cartesian coordinate ground plane produce 0.2 meter per second. But this representation produces a larger error for short-term prediction, because the short-range pixels are projected onto few pixels in a configuration space. Our ego-retinal representation produces about 0.1 meter per second, which means that 1 meter error after 10 seconds. And the prediction is not biased by the short and long range pixels. On the left, we show the image with the ground truth trajectories computed by the structure from motion. In the middle, we visualize the ego-retinal map with the predicted trajectories. On the right, we project back to the first-person image. Our predicted trajectory reflects the human walking preference and avoid the obstacles. Interestingly, it finds a walkable space behind the occluding objects, such as cars. Logically, we cannot make any prediction behind the occluding objects. But our walking preference tells us it is likely that there is a space behind the car so that we can cut through. We can also predict a highly dynamic scene where the car and people are passing by. This is a mall sequence for indoor navigation. Our method reliably finds a plausible trajectory in the presence of a dynamic obstacle, such as humans. This is the IKEA scene. Our methods find a space around the furniture, although similar scenes are not presented in the training data. In this paper, we present a future localization from first-person view by putting yourself into other shoes. We use an ego-retinal map that is a global-centric but seen from first-person view to predict the trajectories. Thank you.